As an OCP member, you have the opportunity to join hundreds of active member companies and thousands of engineers working together to reimagine our world's hardware infrastructure and increase the pace of innovation through a framework of open collaboration. And when it comes to getting the most from your OCP membership, it's critical to listen, understand the community, share your expertise, and build trust. Why? Because OCP isn't merely a place to buy and sell. It's a true community. And like any community, you get out of it what you put into it. By actively participating, you gain better insight into the community, its processes, the challenges that organizations face, the solutions that are currently available, and how the community is addressing tomorrow's growing technology demands, placing you and your organization in a better position to achieve your goals, whether it be marketing your equipment in the OCP marketplace, adopting OCP gear, or building out your own facility. After all, one of the most important benefits of participating in the OCP community is the ability to drive innovation and enhance the hardware and software you rely on every day, not just for your organization, but for the industry and data center ecosystem as a whole. So become an OCP member, participate in projects, add to the conversation, share your expertise, attend events, or run for an OCP leadership position. There are countless ways you can take part in our community and in reimagining our world's hardware infrastructure. Discover them all at www.opencompute.org.
Please welcome back Chief Executive Officer of the Open Compute Project, George Tchaparian.
Thank you. Good morning, everyone, and welcome back. This is our second day of our summit, and it's incredible, really good to be with you. I told you yesterday that we might approach 11,000 attendees. I think we're going to make it. Thank you very much. We have also a good lineup of keynote speakers this morning, executives representing these companies. And without further ado, I am going to also invite Cliff Grossner, our Chief Innovation Officer, to do the opening remarks this morning. So thank you again for being here. It's very exciting to see the collaboration among all of you. And good luck to you, and hopefully you learn a lot. Thank you very much, and we'll see you later.
Please welcome Open Compute Project Chief Innovation Officer, Cliff Grossner.
Wow. Almost 11,000 people here. This is great. Welcome, everyone. I'm so honored to be here in front of all of you. Got a few things I'd like to share with you. First of all, when I think about how things have evolved with the migration from building cloud data centers using traditional ORV3 racks and a power envelope of well under 100 kilowatts, to AI data centers with expectations of hitting 1 megawatt and more, that is well underway. At the center of this transformation is the OCP community, all of you, which is why this year the theme of the OCP Global Summit is leading the future of AI. The fact that there are in the vicinity of 11,000 people here in San Jose for OCP Global Summit speaks volumes to the role of the OCP community in leading the way. Yesterday evening, we heard George talk about how the Foundation's objective has always been to cover the entire open data center ecosystem, covering IT as well as physical data center infrastructure and facilities, applying the unique, open, and collaborative environment of the OCP community to deliver specifications and community-driven standardizations. And most importantly, to take this all the way to product, very unique in what we do. The challenge in front of the community has evolved over the 15 years since the Foundation came into existence. The current challenge is to help building at scale AI clusters and the infrastructure that houses them. As the focus has moved from cloud to AI data center, we have experienced a large increase in the number of physical infrastructure projects and work streams. For example, we recently launched a coolant distribution unit project, and a facilities-level power distribution project, sort of marking the evolution. Now, in response to learnings from the OCP Open Systems for AI initiative and the workshop series that we've been carrying out throughout the year, in addition to a new open letter call for collaboration championed by Google, Meta, and Microsoft, and joined by so many others in the last couple of days, I am pleased to announce a new Open Data Center for AI strategic initiative. Really, the intent here is to increase efforts on key data center infrastructure issues: power, cooling, mechanical, and management telemetry. This expands the OCP Open System for AI umbrella initiative. The mandate for the Open Data Center for AI strategic initiative is to develop standardizations for data center infrastructure, allowing different AI accelerators to be deployed as flexibly as traditional compute in today's cloud data centers. This is a new effort. Please come and join. All are welcome. Let's take a closer look at the Open Data Center for AI strategic initiative focus areas. Power, one of the key areas, is about standardizing the interfaces for high voltage DC systems and defining acceptable thresholds and standards between utilities and data centers. Cooling. Here we'll be looking at coolant distribution units, the design and deployment of them, looking at standardizing the screening and commissioning processes, and eventually working towards a common community-led design. This effort will build upon the Deschutes specification from Google that was talked about yesterday evening, with 5 prominent OCP members already committed to carry out this work. And I'm so pleased to announce that in the few days that the Google specification dropped, we have over 5 CDU-related SKUs added to the OCP marketplace. When it comes to mechanical efforts, when we think about the data hall, we have to think about standardizing key physical infrastructure parameters, rack dimensions, aisle widths, weight-bearing capacity. And if we look to the future, we would like to see enabling robotic-assisted operations. When it comes to telemetry, which we all know is important for management, the community will extend the current efforts to building systems, working on defining standard protocols for physical systems management telemetry, and to eventually enable autonomous control systems to coordinate data center power consumption and load fluctuations. So, very exciting new effort that's getting started. Now, we talked a lot about the new dimensions for OCP yesterday, and I did that this morning. The work of the community also continues inside the data hall. All workloads are complex, and AI ones are even more so. And to achieve maximum performance requires significant investment in AI cluster system design, integration and configuration, and testing, as we heard from Caruso yesterday. To help standardize AI cluster configurations, the community with Broadcom and Celestica as co-leads has launched the Open Cluster Design for AI strategic initiative. Its mandate is to develop AI cluster designs which are detailed enough to provide a technical basis for procurement and deployment. Scale and workload-specific designs for what we call pods will be developed, where pods can be combined to form complete and larger clusters. Pod designs will cover selection and configuration of scale-out, scale-up networking, including cabling solutions. And again, we saw some of the pictures yesterday which tell us that those cabling solutions are non-trivial. They will cover also both air-cooled and liquid-cooled solutions, tapping for different markets. The resulting guidelines and best practices are intended to span small, enterprise, Neocloud, and hyperscale deployment sizes. We've had many contributions and new work streams launched in the last 6 months due to the influence of the Open Systems for AI initiative. George mentioned some yesterday, Deschutes, Diablo, Clemente, the list goes on. I wanted to circle back onto an important work effort that was announced at the OCP APAC Summit last August, in case people missed it. The optical circuit switching workstream, co-led by volunteers from OCP members like Ipronix and Lumentum, with many initial participants including Coherent, Google, Microsoft, and NVIDIA. Open circuit switching leverages photonic technology to route data optically. Google extensively uses optical circuit switching technology in their data centers. And this workstream will allow the others to follow when building AI clusters. Due to the standardized interfaces and configuration APIs that will be brought forward, enabling easy integration of optical circuit switches with SDN controllers and with network management platforms. Okay, been a lot of talk about this $295 billion number that George mentioned yesterday. This is a result of an impact study that we commissioned with IDC, and it's really been a big change since last year. This 5-year forecast is a dramatic increase from the $75 billion from last year. 4 times. Very unusual for a forecast to change that much. I've already had questions about, how come such a big change? Where's the reality in this one? And I can assure you that last 6 months, the IDC analysts collaborating with the OCP team has done the due diligence to speak to vendors, people deploying the equipment, and looked at every nook and cranny and corner we could to come up with the best estimate possible. No one has a crystal ball. 5-year forecasts can change, admittedly, but to reinforce what this means, for 2029, more than 25% of the spend for servers, the largest segment in this forecast, is going to be on OCP-recognized equipment. That means that OCP's community designs will live on for a tremendously long time. Okay, almost done. One more data point, then the heavy lifting is over. $295 billion, the predominant use case, runaway use case for 2029, AI. We knew that, but now we know how big, $155 billion. And we also see how the other use cases line up against it. They tend to start to pale by comparison. So that helps us understand where we set our sails and what's our North Star, at least for now. I'm out of time, and I just want to say in my closing, we have some great keynotes following me, as George said earlier. There's a couple of announcements sprinkled in them that I want you to pay special attention to. One, ARM is going to make an announcement regarding a contribution to the open chiplet economy that dramatically changes the game for OCP. 2, Broadcom is going to talk a little bit more about scale up on Ethernet that is going to be done at OCP. Again, really important that this is coming to the OCP community. And last, we have Denvr Dataworks and Scaleway are going to talk a little bit about a new work effort, a new work stream that is just launched at OCP. But with that, thank you very much. Enjoy the summit. We'll see you.
Please welcome ARM Senior Vice President and General Manager of Infrastructure Business, Mohamed Awad.
Good morning. Good morning. Good morning. Thank you. Thanks to George, thanks to the board, thanks to the events team that puts this amazing event on, and thanks to all of you for being here. It's really an honor. What a crowd. What a time to be in our industry. You know, I joined my first OCP in 2018. I think the crowd here is literally 4 times the size, so this is quite the honor. You know, the world is changing so rapidly right now. It's really no wonder that there's so many people here. It's literally the folks in this room that are kind of making it happen. In many ways, OCP has come such a long way since that first event, and so is ARM. We're so proud to be a part of it. You see, the story for ARM and Infra started at the same time as OCP, way back in 2011. That was the year that OCP was founded. It was also the year that ARM started investing in infra. For us, that meant making our architecture available to the world and investing heavily in software. We were looking to lower the investment required and accelerate time to market. The idea is that people could go launch their own custom CPUs. Over the next couple of years, we learned a couple of things. First, it was a lot harder than we thought. It turns out that it was just way too complicated and expensive for most people to launch a CPU, a brand new CPU platform. The other thing that we found was that hyperscalers were absolutely looking to move away from generic one-size-fits-all solutions, but they needed a platform to innovate on so that they could go build optimized systems. So in 2018, we joined OCP as Platinum members. We launched ARM Neoverse, our implementations and our platforms for the infrastructure ecosystem. And obviously, a lot has happened since then. Today, every major hyperscaler is deploying ARM Neoverse. The world has shifted to focus more and more on performance and efficiency. AI is obviously at the center of everything that we're doing. And we're all trying to keep up with demand. Since 2018, OCP membership has more than doubled. We're at almost 500 members. There's more than 10,000 attendees here today. ARM Neoverse has shipped over 1 billion cores into the data centers. And we're so proud to be part of the board. The ecosystem has come so far, but we are just getting going. The scale of what we're dealing with is absolutely mind-blowing. And I think it's important that we all just take a minute and realize that AI has changed everything. Today, literally today, on October 14th, there will be 4 billion AI queries that are issued. If they were printed on paper, that stack of paper would reach all the way to the International Space Station. That happens every day, and that number is only growing. To support all that, we've had to cram more and more compute into those data centers. This year, we'll add 16 zettaflops worth of AI compute. That's 16 billion trillion calculations per second. If the 8 billion people on the planet were each doing a calculation per second, it would take us 63,000 years to do that much compute. And we're expected to add 160 gigawatts worth of power for data centers by 2030. That's enough power to power 150 million homes, the entire US housing stock. That's amazing. These three things, demand, compute, and power, are so interrelated. You see, demand is obviously relentless. Compute and power are struggling to keep up. And this is all before we've unlocked many of the transformative AI use cases, things like healthcare, things like environmental sciences and physical AI. Whether it's Stargate, Meta, Google, Microsoft, AWS, OpenAI, they're all talking about gigawatts, tens of gigawatts even, and they're talking about it routinely. You know, I love this image. It's of a tent which Meta put up to put a data center in. And I loved the image before I got here, and then I realized that OCP was housing this in a tent because of the demand. Like, wow. And it's still not enough. You see, the industry is hyper-focused because of all that demand on the only thing that matters, performance per watt. Performance per watt of the entire system, the entire infrastructure, the entire campus, the entire data center. The entire system needs to be optimized with that in mind. You see, perf per watt is about keeping up with demand, getting more out of the power you have wherever you can find it. And that means highly tuned system design. You see, back in the day, we built data centers around general purpose, off-the-shelf parts. Everybody knows the story about Google, right? Stanford dorm room, grab a bunch of hardware, stick it in a closet, and get going. Don't worry about things like RAS. Don't worry about capacity. Software will figure it out. We'll just keep adding more CPUs. Well, our thirst for performance, the fact that we're limited by power, has changed all of that. It turns out at ARM, we know a thing or two about performant, efficient design. It's in our DNA, from architecture to implementation to system design. It's who we are. In fact, long before we shipped our 300 billionth processor with the ARM technology, 30 years ago, our first product was a super efficient, system-optimized custom CPU for a product called the Apple Newton. You see, efficiency and performance per watt certainly starts with the architecture and the IP, but it does not stop there. It requires comprehensive system design. That's the only way to keep up. In the age of AI, the world's largest tech companies are all optimizing all aspects of the system, from data center to pod to rack, all the way to the chips that make them possible. Whether it's Meta, Microsoft, AWS, Google, NVIDIA, Broadcom, systems aren't being built with off-the-shelf parts. They're being built with custom silicon specifically for these AI data centers. Optimized acceleration, optimized compute, optimized networking. And they're doing it for pretty simple reasons. So they can target the constraints of Amdahl's law across the system, so they can deeply embed key features like security and RAS, and most importantly, so they can co-design and architect the system for performance per watt. Whether it's expanding the scale-up network, creating a coherent memory domain between CPU and accelerator, or optimizing the die-to-die interface for HBM, custom silicon is allowing them to maximize performance within a given power envelope. OCP has been involved in many of these areas, but together, I think there's an opportunity for us to do more. See, silicon is not for the faint of heart. Building a new chip can easily cost over $1 billion. Multiply that by all the chips needed in the system, and you're talking about some big numbers. But the reality, in this environment, the money's not the difficult part. There's plenty of money flying around. It's the time, it's the talent, it's the risk. Things are just moving too fast. Things like verification and architecture design and software, they can be incredibly taxing on an organization. In a market moving this fast, you want to focus investments where they matter the most. You see, helping focus investment on what really matters has always been the mission of both OCP and of ARM. When someone needs a piece of silicon, when somebody wants to buy a piece of silicon, someone needs to consume a piece of silicon, they have this decision to make. On one hand, they can take something off the shelf, which isn't necessarily optimized for their use case. On the other hand, they can start with an architectural implementation and build from the ground up. That gives them the ultimate flexibility. But the reality is that they have a choice to make. You see, there's this trade-off between time, complexity, and cost versus how much customization you can possibly achieve. And the interesting thing about this chart is that the x-axis is linear, but the y-axis is exponential. Neoverse is a great case study for this. When Infra, we started our focus on architectural implementations, but things didn't really start to take off until 2018 when we invested in creating an implementation specific to infrastructure that hyperscalers and the ecosystem could take and innovate on. Because we lowered the cost associated with building those solutions, we brought the complexity down. We brought the time to market down. Today, within the broader OCP community, there are solutions for every point along this continuum. There are ARM solutions at every point along this continuum, but there are solutions from other architectures as well, and that's the point. You see, the point is choice. Choose what makes the most sense for your particular use case, based on what you are trying to build. Everybody wants that bottom right-hand corner. Maximum customization, lowest risk, lowest time, lowest complexity. What we have learned at ARM over the years is the best way to get closer and closer to that point is with ecosystem. That's why 2 years ago at OCP, we launched ARM Total Design. This is an ecosystem centered around compute subsystems that helps get solutions to market quickly and more affordably. ARM Total Design includes foundry partners, it includes EDA partners, it includes design services partners, it includes firmware partners. They're all building expertise around CSS and can help bring products to market quickly. And ATD has grown rapidly. In the last 2 years, it's tripled in size. In fact, we have a bunch of new members who joined within the last year or so. Many of them are showcasing some of their work within the OCP marketplace. It's an incredibly collaborative group. In fact, when we brought these companies together, an interesting thing happened, which often does when innovative companies get together. The ecosystem started working to fill a gap. They started working on chiplets. You see, chiplets enable integrated SoC system design without all the complexity of having to build the entire silicon yourself. You can focus on the differentiation and leverage the ecosystem for parts which are less differentiated, which you don't necessarily want to invest in. ASIC partners found that with CSS and ARM Total Design, they could easily build chiplets that both validate their capabilities, but also accelerate time to market for their customers. They could enable a lot of reuse, they could enable a lot of leverage, and they could amortize the investment across lots of different customers. So I know what everyone's thinking. Chiplet marketplace. Whenever you talk about chiplets, you talk about chiplet marketplace, right? The world's been talking about chiplet marketplaces forever. This idea that you can go to some website and pull a bunch of chiplets, order them, they're going to show up and you're going to Lego block them together. I get news for you, we're not there yet. And we might never get there. There's so many challenges with it, everything from business model to security to shoreline. That's not lost on me and it's not lost on most of you, but it doesn't mean that we can't work together to help streamline the entire development process. You see, people have been using chiplets within single organizations for a long time. They've been reusing them within single organizations for a long time. And now, more than ever, we're seeing multi-vendor solutions emerge between companies. See, it allows for tremendous flexibility. It allows for time to market advantages. It's unclear to me if we ever get to a truly interoperable chiplet marketplace. But there's no reason we can't work together to define a common system architecture. This would meaningfully accelerate time to market, and it would meaningfully accelerate innovation. It allows for new dimensions of systems optimization, which are too complex for most companies to take on by themselves. So it's in that spirit that we brought the ecosystem together and started to sketch out what a more uniform chiplet system architecture could look like. And so in January of this year, we launched what we call the ARM chiplet system architecture. We've been working on it collaboratively with about 70 partners across infrastructure, but also markets like automotive and industrial. CSA is focused on creating consistency across designs. We work together to define things like chiplet-based SoC architectures, interface definitions, protocol mappings. We leave the ecosystem to figure out what the exact interface looks like or the shoreline needs to look like. But the idea is that there's a common basis for communication and companies are speaking the same language from day one. CSA makes cross-industry collaboration that much easier. We're seeing lots of interesting projects emerge. We've seen companies that are focused on things like I/O, acceleration, or even general purpose compute come together to build full-on SoCs. And we're seeing tight integration between different players in the ecosystem. You see, as AI racks and data centers and warehouses struggle to support more and more performance per watt and denser compute requirements, the integration point for heterogeneous compute is changing. It's moving from the board to the SoC package. You may have heard the package is the new motherboard. Yeah, chiplet system architecture with ARM Total Design has made great progress. But when we look at the OCP server work group and the amazing work it has done to move the industry forward, with modular server architectures, specifically with the data center modular hardware system, we can't help but think that we need a similar approach to AI silicon design. That's why we're contributing the work we have done on CSA to OCP. At ARM, we believe deeply in the potential of an open chiplet ecosystem, and we think OCP is the perfect place for us to continue advancing the work. The next generation AI infrastructure is not going to be one size fits all. It's going to be optimized from the ground up. And as part of the contribution, we'll be asking ARM Total design partners, many of them whom already are working together and already have I/O, acceleration, and CPU chiplets based on the foundational chiplet system architecture in the works, up here on the slide, to join us. And to be clear, FCSA is compute architecture agnostic. We'd love to see the entire ecosystem join us, the entire OCP community. We're truly living in an amazing time. ARM is incredibly proud of the work happening at OCP, and we're honored to be a proud of it. Thank you for your time this morning.
Please welcome Broadcom Senior Vice President and General Manager, Core Switching Group, Velaga.
Good morning. Thank you, Mohamed, for that excellent presentation. Between yesterday and this morning, you've heard a lot of news. And if you look at the last couple of weeks, one single company has announced 10 gigawatt data centers, plus another 6 gigawatt data centers, plus another 10 gigawatt data centers. You're talking about a single company over the course of 4 weeks announcing about 26 gigawatts of data centers. If you think about it, 26 gigawatts of data centers equates to roughly about 15 million, XPUs. By the way, during the course of my next 15 minutes, when I refer to XPUs, they could be GPUs, TPUs, or somebody building their own accelerators. So I just want to make sure everybody gets that nomenclature understood. Now, when you think about it, why are people building so many data centers, so many gigawatts, and building this massive infrastructure? It's because machine learning and AI is a distributed computing system. And we've actually talked about this 3 years ago, which is, at the end of it, no one XPU is large enough to handle the workload that needs to be done. And you have to have many of these XPUs stitched together, and that's where the network plays an extremely important role. And the network is the computer. And 3 years ago at OCP, we took the position that the networking technology of choice is Ethernet. And at that point in time, there was another technology people thought was the only way to build AI clusters. And we said, no. It has to be Ethernet because Ethernet is open, it's resilient, and it's very economical, right? And with that in mind, I want to kind of share with you the advancements in Ethernet that have happened over the last couple of years. And true to what we promised 3 years ago, what we've been able to deliver in the marketplace. So if you look at it, in terms of an network for AI, there is obviously the scale up, there's a scale out, and there's a scale across these data centers. Ethernet is the only technology. I'll say this one more time. Ethernet is the only networking technology that actually cuts across all of these, across scale up, scale out, and scale across data centers. I believe in Ethernet so much that I carry this Ethernet cable in my pocket today to show you. Something as simple as this is the only way you can build a machine learning cluster that's large enough. By the way, it's very hard to find. It's very easy to find somebody who can work on Ethernet technologies. Very hard to find somebody who's going to work on all these other esoteric technologies that people have pitched as the way to build machine learning clusters. Now, when you look at scale up, one of the things to think about it is why there's so much talk about the scale up and what's going on in the scale up. And really what scale up is trying to do is it's making sure that when you have multiple XPUs, the HBM memory on one XPU is available to another XPU, right? And when you think about what's happening, the amount of bandwidth that each XPU today has with the HBM attached to it is about 40 terabits today, because it has 4 HBMs, each running at roughly 9.6 terabits per second. Tomorrow, you'll see 8 HBMs, each running close to 12.8 terabits per second, over a total bandwidth of 100 terabits per second. So when you have two XPUs and you want them both to talking to each other and it goes over a network, you want to make sure the network has that very high bandwidth to facilitate this, right? That's number one when you think about scale up. Now, here is where Ethernet comes to play. There's been discussions yesterday you've seen in the keynote about ESUN. ESUN stands for Ethernet for Scale-Up Networking. And here's the beautiful part about it. As I said, Ethernet is the only open technology, truly open, by the way. And I'll show you why it actually makes a big difference here. On the top of this picture is accelerators, XPUs. And I've just put them as A, B, and C, right? A is one company is making it, B another company is making it, C another company is making it. Because if you think about it, if the world has 15+ million XPUs being bought by a single company, you don't want to have one vendor that's making these XPUs or GPUs or whatever you want to call it. You want a heterogeneous environment. Otherwise, we'll be living in a massive monopoly. So when you have these different companies making these XPUs, think about it. There's all engineers in these companies. They all have their own inventions. They all want to move at their own pace. The last thing they want to do is wait for somebody else to write a specification on how that XPU is going to do scale up. So when you look at any other alternative technologies outside of Ethernet, they try to define what happens in the XPU and then what happens in the link, whatever you want to call that link. But Ethernet does it very differently. What it does is it does a clean demarcation between what happens in the XPU and then what happens on the Ethernet networking layer. By doing so, what you're able to do is let all these XPU companies compete on the merits of their own XPUs, innovate, and essentially do the scale-up the way they see fit in terms of how they're going to schedule the traffic, how they're going to handle the memory semantics, and how they're going to handle the software layer that sits on top of it. And in the meantime, the Ethernet layer underneath is very simple. It's all either standards-based, existing specifications-based, nothing proprietary. Okay? That's extremely important. Ethernet, open, nothing proprietary. And here's the thing I will tell you. When somebody says it's open, you should not see words like, I am a certified platform, right? Or my NIC only works with my switches. Those are not what you should be seeing. You should truly be seeing a truly open interface. And that's what Ethernet brings to bear. Because of that, there is an agreement in the industry that says, look, Ethernet for networking is the best technology for scale-up. And let's all agree on it, and let's standardize on it based on existing specifications. And let everybody go build their Ethernet switches. Let everybody go build their XPUs as they see fit. And that's what the companies have come together here. If you look at the names of the companies here, these are all companies who are leaders in their own rights in the markets that they're playing in. And they've all collectively decided that we can make Ethernet work for scale-up networking, but more importantly, there's nothing new to be made. It's existing Ethernet. And they're working towards accelerating the adoption of Ethernet for scale-up. So one more thing here. Again, the beautiful thing about Ethernet, it decouples what happens in the XPU from what happens in the network, and you can use existing Ethernet switches, both that have been built and will be built to do scale-up. And that's the very powerful part of it. And to facilitate the scale-up, it's not just about building the silicon, building the hardware for it. We also want to make sure that there is software for it. And so there's a work group that's being formed in OCP to make sure the software that is needed for scale-up Ethernet is available, and that's a version of Sonic. Just kind of think of it as a stripped-down version of Sonic with very specific features optimized for scale-up. So the ecosystem of scale-up on Ethernet is here and available. Now, one of the questions that, that have come up in the past is, well, we know Ethernet is open. We know Ethernet is ubiquitous. We know it has high bandwidth. But can it achieve the lower latencies that might be required for scale-up use cases? And it can. And this is actually a slide that shows that you can achieve sub-400 nanoseconds latency for data traversing from an XPU through a switch back into an XPU. So nothing about Ethernet limits its ability to build the lowest latency interconnect that's available. Now, the next question that comes up is, OK, today we are limited on what we do on scale-up to about less than 100 XPUs inside a rack. But when you actually go talk to the people who are developing these large language models, they want to see a scale-up that's a larger domain, beyond less than 100 to a couple of hundred, potentially even kind of going to 1,000 plus. There's only one networking technology that has been proven in the marketplace for decades that can reliably scale across rows, across data centers, and that's Ethernet. So we will deliver low latency on Ethernet. We will deliver the reliability on Ethernet. And we will actually increase the size of the scale-up domains beyond being constrained to a physical rack and the limitations of copper inside a physical rack to go across racks. To do that, obviously, what you need to do is have Ethernet switches that are continuing to increase in bandwidth. And all I'm showing here is an example of us as Broadcom being able to double the bandwidth every 18 to 24 months. But that's the beauty of this Ethernet marketplace. There's a significant competition that it forces all of us to be on our toes and deliver the best product in a truly open fashion as fast as we can and keep moving this industry very fast. And when you have this kind of a bandwidth, we've talked about what we can achieve in scale-up. But also let me touch on what we can achieve in scale-out. There was a presentation yesterday from Oracle, and there was something very profound out there that said, look, when you build a very large domain size, the big benefit that you get is you actually increase the utilization of the system, and you get far more efficiency by building larger and larger clusters. And shown here are two possible ways you can build a 128K GPU cluster. One that uses a 50 terabit switch, and another one that uses a 100 terabit switch. And what you find is when you double the bandwidth of the Ethernet switch to 100 terabits, you reduce the number of layers in the network. That reduces the congestion in the network, reduces the number of optics, reduces the number of switches which are needed, reduces the amount of latency that is occurred through the overall network. And all of this is great for job completion time. Think about it this way. A 100,000 GPU cluster is probably going to cost you a minimum of $3 billion, depending on how well you negotiate. The network for the same thing, an Ethernet network for it, is probably going to cost you less than $100 million, excluding the cables and the NICs which are needed. So if you can build a high-performance network, and there was a presentation that was done a couple of years ago that if a network is not done right, you can idle your GPUs for 50% of the time. So by building a high-performance network, the network pays for itself. And the only high-performance network, my friends, is an Ethernet one, because it's truly open, it's truly competitive, and you can see in the marketplace today that Ethernet has a lot of choices and advancements. And talking about advancements, one of the things that I want to share with you is to get the bandwidth out of these switches, obviously you have copper and as one of the options to get it out. But increasingly, as you go for further distances, you want to go on optics. And when you choose optics, you have a choice of pluggables, LRO, linear pluggable optics, or you can go to near packaged optics or potentially co-packaged optics. There was a recent paper published by Meta that actually has tested reliability of co-packaged optics for about 1 million hours. And they found that the co-packaged optics are actually more reliable than pluggable, for a host of reasons, just the way the box is integrated, to say the least. Now, Broadcom is on the 3rd generation of co-packaged optics. Third generation. For those who thought co-packaged optics just got announced last year, it's wrong. We're on the third generation of co-packaged optics. And again, in the spirit of openness, Broadcom switching platform not just supports our own co-packaged optics, but we also have co-packaged optics from our partners like NTT that we support. One of the other things I want to quickly touch on here is 3 years ago when we talked about scale-out and how Ethernet could be done on scale-out, we were working with the Ultra Ethernet Consortium to improve the performance of RDMA on Ethernet. And one of the things we needed to do was actually have a NIC that is capable of doing advanced RDMA functionalities that is compliant with the Ultra Ethernet specification. Today, Broadcom announced our chip, which is called the Thor Ultra, which is the industry's first true 800 gig NIC. This is not a NIC that has two 400 gig flows pretending to be an 800 gig NIC, but it's truly an 800 gig NIC. Two different form factors, either 8 by 100 or 4 by 200, that will deliver all the Ultra Ethernet compliant features, specifically focused on enhanced RDMA, right, which is multipathing, out-of-order placement, selective retries, all the things which are needed to build hundreds of thousand GPU clusters for scale-out with RDMA. And the one thing I promise you on this NIC, it will not say if it is not connected to a Broadcom switch that the functions are going to degrade. It's truly open. The adaptive routing functionalities, the advanced RDMA functionalities, you can connect it to any Ethernet switch in the world. It'll deliver the same features. You can connect it to any cable in the world. It will not degrade performance. And you can connect it to any XPU. It'll work fine. And that's truly what's the benefit of Ethernet, which is open, interoperable ecosystem and technologies. And then obviously we talked about scale up, scale out, and you have to go across data centers because oftentimes you don't find 1 gigawatt of capacity in one location. And that's what we are able to do with deep buffered switches. So I want to rest my case by saying Ethernet is the only technology that can cover all the use cases for AI, from scale up to scale out to scaling across data centers. And there's going to be products available from a multitude of companies in this space. You probably already have heard and will hear from them. And the entire suite of technologies which are needed, either on the host side, the NIC side, or those Ethernet switches, are available on Ethernet. So I want to leave by saying the network is the computer. Ethernet is the only way to network. And it truly is the most open, efficient, and reliable networking technology that's out there. Thank you for your time.
Please welcome Dell's Senior Vice President and Chief Technology Officer, Ihab Tarazi.
Hi, everybody. It's always awesome to be at OCP, my favorite event. Everybody here speaks the same language of technology, and everybody here is interested in making things move and collaborate. I want to share a little bit today with you what Dell has been doing with OCP. We had a long-term engagement, and how we leveraged OCP for the most advanced AI HPC clusters. So our OCP engagement has been long, and we have deep engagement in many, many groups, and also contributions. We started about 10 years ago with some of the engagement around OCP NIC and all the specifications, both for networking and storage, that we embedded in our servers. But we upped our engagement significantly a few years ago when we started with this community and some of the big players to define the future of compute. And we were one of the many, we're not the only one, but we were a significant contributor, and we contributed tremendous amount of designs for DCMHS, which is redesigned completely how compute platforms are developed. Probably more importantly is once we defined the specifications, we put all our investments and changed our entire roadmap and products to be DCMHS capable. So now we have one of the most modular compute systems anywhere in the industry, all based on DCMHS, and we continue to put it into all our future servers, that require that technology. So to us, that was tremendous collaboration, and it paid off significantly in speed and scale. So thanks to the community, we couldn't have done it without you here. Thank you. And then we started after that to work on the next thing, which is rack scale design. And this is ongoing. And I want to tell you a little bit about what we've done with that. So we started with the rack scale design. That includes many more complex technologies. Liquid cooling, it includes how you design all the cabling, the actual open rack itself, and then how do you embed all the different technology in it. So that continues to be work in progress. I want to tell you how we used it, but also I would say you could see we engage in the cold plate work group, in continuing to work on the open system for AI, which is a starting initiative, and many other areas. Also, we're a key player in Sonic, and when Sonic came to OCP, we just upped our investment. For us, that made it all work. Both the infrastructure and hardware and software all open based on community collaboration. That's what we really believe in. So OCP is definitely the place to be. What we see right now is that CPU continues to go up in capacity and how much thermal is needed. But on the GPU side, it's exponential. And this chart probably underestimates what we're going to be. If you think about it, every single GPU that was announced, by the time it actually came out, the power was up to another 20, 30, 40%. So we're looking at tremendous amount of thermals coming out of the packaged systems. So I'm showing you this chart. I'm sure you've seen few of it, because that changes the entire mentality and design objectives of all data center infrastructure. And we're designing for significantly higher trends than this because we know where this is going to go. We have deployed significant amount of GPUs globally for many, many customers. All the big logos you know about we're working with. And it was kind of interesting to watch how the AI boom happened. At the beginning, people were talking about 4,000 GPUs. What am I going to do? This is like 10 megawatt. I'm not going to find 10 megawatt anywhere. And what do I do with it? And the density. Quickly, the discussion moved to 18,000 GPU clusters last year. This year, we have some customers, many customers already working on 110,000 GPU data halls. But for the most part, a lot of people are between the two. What is interesting just the last 2 months is the scalable unit. And if you remember, the scalable unit used to be like 8 racks. Most people are talking about the scalable unit as a 40 megawatt. So more people are saying, I want to be deploying in 40 megawatt components. That's a scale and scope of tremendous exponential growth. And this chart probably significantly underestimates where we're going to go next. So you wake up in the morning, you say, like over a weekend, you'll be having discussions with multiple customers. All of them are saying, I need 40 megawatt here, I need 40 megawatt there. What does it look like? What's the networks? What's the optics, liquid cooling? That's kind of the industry discussion when it comes to this big AI deployments right now. So what have we done to make that possible? How have we responded to these kinds of requirements and deployments? First, we looked at the OCP, liquid cooling system design, and we've spent a lot of time on that because liquid cooling is the basis for lots of these high GPU deployments. You can't do it with air-cooled. And for us, the big technologies that we're innovating in, and we have been innovating for a few years, were the manifolds. What is the flow rate? How do we support higher flows so we can get more capacity into the same rack? Obviously, the cold plates, the thermal interface material, all these components. The CDUs, we innovate significantly with partners as well as build our own CDUs. And then the quick disconnects, we've learned a lot from many people in this industry here of the durability and capacity of quick disconnects. But the key here is this has to come in as a single system to get the performance and to get the reliability that you need and be able to support the higher thermals. In addition to building the system, what we've experimented in early last year to be able to get thousands of GPUs, we've relied heavily on rear door heat exchangers. And you could see it in this chart here all the way to the left end, where rear door heat exchangers allow you to be able to put GPUs in a data center even if you don't have chillers. And people can't get chillers most of the time now. There's a long waiting list on them. So rear door heat exchangers became very significant to ability to deploy. But as you can see, you still have to put cool water in it, about 20 C, and they still eject cool air into the environment, so there's some reduction in efficiency. We've gone and designed a rear door heat exchange enclosure where the whole rack is now fully enclosed, and that lowered power consumption by another 60%. What's more important, you can put non-chilled water into it. We're deploying this in some of the major, very high-dense facilities right now. To me, this is the new data center. Significant amount of capacity in one rack, all enclosed. It has its own heating, and cooling enclosed, and it can withstand being put in any facility that doesn't have to be a purpose-built data center. So that is the next technology to enable us to get the density, get the efficiency, and manage through, the power consumption. The Open Rack ORv3, we are a huge consumer of this system. We started about 3 years ago, and what I think works really well in OCP is to take the specifications and enhance it, modify it for what you need for specific use cases, and then contribute what you think makes sense to contribute. In our case, we started with ORv3. We made these kinds of changes. We changed how we connect the CDU to it from a DLC to create much better performance. We enhanced significantly the bus bar for the power. We enhanced the quick disconnects and how you connect. And then we added more cable trays for operational speed and efficiency. And then what we ended up with here is a 480 kW capable rack that we're already deploying. So this is probably the most dense ORv3 rack you can find. We designed it not only for capacity and efficiency, but for operations and serviceability. So with this deployment, we have been able to deploy 50,000 GPUs in 6 weeks on an ongoing basis, or 100,000 in a few weeks more for customers. You couldn't have done it, this density, this operational speed, you couldn't have done it with something other than ORv3. We have hundreds of thousands of GPUs deployed today with ORv3, probably some of the biggest deployments of OCP systems anywhere. Thank you. Yep. And now, what we did is we embarked on a journey 3 years ago to transform and modernize HPC systems. HPC systems were all designed to be what I would call custom-built snowflakes, 5-6 year process, and every time you get a new system, it's a forklift. You take out everything you had before, and you start with a new system. We partnered very closely with Berkeley Labs, Department of Energy, and we just won the most advanced HP system anywhere. And these are the specifications of the system. It's a 480 kW, all OCP, all open, both from a compute, where we were able to get 27,000 cores in one rack, as well as 144 GB200, and it will also be VR200 and VL4 in one rack at 480 kW. So what did that do to them? Number one, tremendous advancement in technology and density. This is going to be the most advanced OCP system. Number two, they don't have to wait years. A new chip comes out, it's all modular. You can mix and match, you can add capacity anytime. And we're doing the same with the University of Texas at Austin supercomputing. So that changed HPC forever, not only for the big labs, for governments, sovereign cloud, as well as for all the different industry HPC systems. We couldn't have done it again without OCP, first OCP HP system out there. And then on AI, we've done the same thing. We built modular platform, both based on NVIDIA, B300, GB200, GB300, and in the future, VR200. And then also with AMD, we innovate significantly. So we have MI355X, and in the future 450. all in the same OCP rack. While it says 480 kW, which is what we have today, this system is upgradable to 1 megawatt. So we'll be able to get to 1 megawatt systems with the same OCP and be able to support compute, AI, HPC, and networking, which is also going liquid cooling. So just to close here, we're a huge partner of OCP, a huge contributor. This community is critical to our success, and we have strategically and consistently contributed, engaged in every component. Most of our systems now are leveraging OCP specs for everything from server design, rack design, optics, and we look forward to some of the announcements here, both on the scale-up that Tom talked about before, and also as well as all the different capabilities that are needed for liquid cooling, CDUs, and an open AI system. Thank you very much. This is a great community. We're happy to be part of it. Thank you.
Please welcome Open Compute Project Vice President, Market Intelligence and Innovation, James Kelly.
Good morning. So the next two keynotes that I have the pleasure to introduce are related, and they're also very strongly related to this year's summit theme, Leading the Future of AI. You've had a great orientation when it comes to AI today, hearing about the Open Systems for AI strategic initiative, the umbrella that connects all of our projects, as well as some new strategic initiatives related to AI, the Open Cluster Design for AI, the Open Data Center for AI. It was initiated by the hyperscalers with that open letter. And the hyperscalers are absolutely the longtime regulars in our OCP community when it comes to driving AI. But there's this new cohort of cloud companies that are deploying infrastructure and platforms as a service with GPUs and other accelerators, right? And they're on the rise. They're really important in our community. Of course, I'm talking about Neoclouds. Neoclouds, or emerging hyperscalers, as they're sometimes called. I think they like to be called that. They're this really important and new part of the OCP community and industry, too, that we really absolutely want to welcome. There's a lot of common ground to harmonize between the Neoclouds and the rest of this community. And the Neoclouds are absolutely deploying tons of OCP-recognized IT equipment. They really know us for the IT specifications that are coming out of this wonderful community. And as you heard, in building so many new data centers, they're absolutely interested in facilities construction, in sustainability, in the grid interface, and the power distribution, the cooling distribution, and standardizing the management interfaces that are going to tie together and orchestrate the entire dynamic AI data center. So the Neoclouds, in summary, are deploying cutting-edge, fast-evolving AI infrastructure, but uniquely, they're doing it at small scales and massive scales. They're doing it in all of these new geographies and with new constraints. So I'm pleased today to introduce the launch of this new workstream at OCP. It's called Scaling AI Clusters at Neoclouds, a little bit on the nose. It's co-led from volunteers from the companies of Scaleway, Denvr Dataworks, and Farm GPU. I would encourage you to find the page, look for the QR code in the next couple of keynotes, and join the mailing list. We're kicking off the work stream here today. We've got some featured presentations across all of our breakout sessions and panels from these great companies and other Neoclouds as well. And right now, we have two keynotes from Scaleway and Denvr Dataworks to share the story of their journey with OCP and talk about the unique challenges that they faced and overcome as Neoclouds when it comes to deploying and building AI.
Please welcome Scaleway Vice President, Hardware Engineering, Stéphane Dutilleul, and Scaleway Office of the Chief Technology Officer, Yann-Guirec, Manac'h.
Good morning, everyone. Let me start with one fun fact. Yann-Guirec and myself joined the company the same week, a couple of years ago. And 4 years ago, we attended our first OCP Global Summit together. So it's very special for us to be here today. You may not have heard about Scaleway, so let me give you some insight. We are part of Group Ihab, which is the 5th telco company in Europe. We are a Neocloud, yes, but not only. We are operating thousands of GPU in Europe, but we are also providing a full public cloud offering based on bare metal, cloud services. Over the last 20 years, we are building our cloud across Europe. And we are coming to the US quite soon in a European, open, and transparent way. And this cloud is built over a dozen of thousands of servers. I could spend a lot of time on this slide, but all in all, at the end of the day, we are all here to talk about bare metal, right? So let's move forward. In order to operate this very large and diverse install base, we are facing a lot of challenges that we all know. SKU diversity, power and cooling efficiency, firmware management, and so on. Some years ago, we had the opportunity, because open source is in the DNA of Scaleway since the very beginning, we had the opportunity to investigate open firmware, and especially OpenBMC, how OpenBMC could help with our firmware management on this large install base. Then we had the opportunity to join some working group to investigate the MHS solution, form factor, serviceability, front I/O, and so on. The next step for us has been to see how OpenRack could help in our journey to OCP. What are the challenges? How is it easy to go to production with this? How it addresses our challenges with regard to power, cooling efficiency, serviceability, maintenance, and so on. We looked at the existing solution. We have developed our own solution to address our very specific needs. We needed switch adapters, filler panel, bus bar connector, and more. And the next step, the obvious next step, I would say, was to investigate the 21-inch chassis, because it makes more sense to use the MHS format into a 21-inch chassis for us. So we had the opportunity to talk, collaborate, voice, provide our feedback to some vendors to find the right form factor for the 21-inch chassis. And at this stage today, we are about to release several products based on OCP or open solution. Like I said, 4 years ago, it was only the two of us. In the meantime, we have invested resources, time, money, but also human resources and technical resources. We have built a team to investigate, but also to develop solutions. But because we don't want to be only in the audience, because we want to be part of the solution, because we want to take some control at some point, we are sharing with people. At OCP Summit, we built a Prime Day user group and conference in Europe, having a lot of people from Europe and the US, companies. And we are also hosting a conference in Paris, AI Pulse, dedicated to AI solution. Okay, that's the state of the art as of today. So the next question would be, what's next? So, YG, what's next?
Yeah, thank you, Stéphane. I still vividly remember first of the discussions that we have in the first week, and we were already talking about everything open, what can we do, and how can we go around that. So let's talk a bit about what's necessary for us as we see it in the industry today. I would say the first part of everything is really on the collaboration between all of us, because at the end of the day, I'm discussing with a lot of other kind of next wave hyperscaler, Neocloud, or any kind of name you want to get us. But we all have the same families of problem. We all have similar way of expressing it and getting answer, but it's all a bit different, a bit not the same way of saying everything, and all of our supplier and upstream don't really mesh up that we need the same things at the end of the day, and really what we want. And it's the same for us on AI and pure cloud and compute around. It's the reuse of the same design, the cross-industry collaboration to be able to have something easier for us to deploy, to use, and to manage for the next 7 to 10 years at a hardware level. And to that, we need to be able to do what we do today with Stéphane and his team, being able to share our findings and what we do around to be able to have something global and the same speech forward to the industry, being able to increase the adoption of all of this solution, decrease overall cost and TCO for all of us, because at the end of the day, we all want the same thing, better TCO, lower cost of ownership, and being able to increase the adoption of the open solution. What does it look like for us really around? Let's start with the zooming out level, because when we started in the industry 20 years ago, we were thinking server by server, and it's really around, yeah, let's put a few servers in this rack. It's going to be 2 kilowatts. It's going to be OK. Today, we are talking rack by rack, and it's mostly 7, 10, 12, 20 kilowatt, 120 kilowatt, even a megawatt at some point, which is a completely different way of thinking everything. When you are deploying on 3 kilowatt racks, you kind of don't care. You put the racks there and it's working. When you are thinking about 20 kilowatt rack, it's a bit more complicated. You need to think about a row, a corridor, a room. And when you go beyond that, you need to think about a data center, a building, or a campus or building, which is a completely different way of thinking about it. And that said, it's very interesting for us as well, because as Stéphane said, we're a Neocloud with lots of GPU and AI stuff, but not only that, we also have all of the traditional cloud, even just bare metal server, very kind of entry-level CPU around that need to run at the same time. And at the end of the day, all of these challenges that we have, it's all the same one. We all deploy bare metal, we all orchestrate bare metal, and somebody at some point create all of the layers around to be able to have a product around. It's the same idea around. And for us in Europe, I heard somebody talk about it as well. We are not going to build a campus of like 25 gigawatts because it doesn't make sense. Everybody in Europe, it's a very fragmented market. It's very complicated to coalesce that market around. It's a matter of size because every country wants their data, their AI, their everything in the country. And if you take France, Germany, Italy, yeah, we can't have like 25 data centers in each country to be able to serve all of the locality around. There's also a very complex energy market in the EU, which is kind of the last power generation that is up, that is going to dictate the pricing. So it's not that fun around for us on the electricity price and being able or unable to do PPAs around. And we also have a very, very strong sustainability goal as Scaleway and Ihab around on one part, and as well our customer. And we need to be able to answer that, and we need globally as an industry to reduce our energy and water usage to be able to be more sustainable for everything that we do. That being said, my call to action around is let's be bigger, all of us together on the hyperscaler next wave. Around, we need to be able to talk from a single voice to everyone. And if we're able to do that, we're going to be way bigger than just trying to make everybody understand what we do. We need to think from the data center up to the software, because it's very important for me that we need to think globally, a holistic approach from building everything, the bricks and mortar, up to the software that is going to run everything to be able to have a global solution and something that is going to seamlessly integrate in an open way around. And please participate in the new FTI workstream scaling AI cluster at Neocloud, which I'm very happy to be able to co-lead for Scaleway. And if the QR code is not working, I'm pretty sure you know where to find everything. Thank you.
Please welcome Denvr Dataworks Executive Officer, Advanced Data Center Technologies, Amy Short.
Hello, everyone. It's great to be on stage with you here at OCP. And thank you to the OCP Foundation for inviting special stage space for the AI Neoclouds today. I think this is a really exciting environment, but also it's a really exciting new industry expanding where innovation and collaboration really are going to be at the forefront. So Denvr Dataworks was founded in Calgary in 2017. And we have a very clear mission to actually accelerate what is next in AI. We are an AI Neocloud, and what that means is that we serve purpose-built AI solutions for AI customer requirements. We're also vertically integrated. So while we're serving those startups, those enterprise organizations, and those researchers, we have a hand in actually designing, operating, and providing services across the entire stack, from the infrastructure to the hardware to the actual cloud experience. So for us, our critical deliverables are making sure that we're serving our customers by providing high efficiency and high performance solutions across that entire stack. When organizations think about AI, the hardest step is often the first one. Where do you start? Regardless of whether you're a developer or a consumer of this technology, it's a really difficult question, and it's almost always immediately followed by, how do we generate ROI quickly? This is a very expensive place to participate as well. So at Denvr Dataworks, what we strive to do is actually shorten the time between the investment and the return. So there will be two different AI challenges that I'll show to you, and these cover the span, I think, of representative challenges that AI neoclouds face, but also might resonate with a lot of people in this room. The first challenge is infrastructure. We all know that AI demand is growing faster than the capacity can keep up. This map from NREL was recently published, and I think it does a really great job of showing the constraints along with the opportunities related to infrastructure. It shows things like power availability, utilities, network, water, land, and if you imagine an additional requirement, which is the regulatory and compliance outlook overlaid all of this, you can start to appreciate not only do we have an energy-constrained environment that we're working in, but also there's a geographic constraint that we have to work in, and these also are going to start impacting the amount of time that it takes to build that deployment. Globally, AI data center capacity is projected to grow tenfold in the next decade, requiring trillions of dollars of investment. So the challenge isn't just building fast enough, it's actually building efficiently. So this is an area that's ripe for innovation. Denvr recognized very early on that we need to think differently about how we approach technology at the infrastructure layer in order to optimize for that efficiency, allowing ourselves to actually deploy with a lot more agility to meet this evolving market need. From the infrastructure challenges we just saw, modular designs are a game changer. What if you could deliver your data center on the back of a truck? What if you could drop that data center in the middle of a parking lot and connect it to stranded power, all within 6 months? A game changer, it really is. So here what you can see is an example of a Denvr modular data center that's based in Calgary. It's in yellow. It's shown in the forefront of the picture. Behind it, what you see in red is a traditional air-cooled co-location facility. Now, there are different workloads, different customers, different hardware being served in each of these different environments, but the difference between the density that you're able to achieve when you innovate in the way that Denvr has is striking. So this air-cooled colo in the back can serve about 1 megawatt per 6,400 square feet, whereas the Denvr Dataworks data center in front can do the same in just 600 square feet. So that's a 10x density advantage. To de-risk operations, we build flexibility into our cooling environments as well. I know many people in the room have cooling as a huge priority for them for current and next generation development. Our modular designs can support immersion or direct-to-chip cooling designs as required. You can see here in this image an example of our earliest deployment, A100 SXM servers, and you might be thinking to yourself, why in the world, Amy, are you talking about A100s at a tech conference? We've moved so far past those. The reality, though, is that these servers were deployed 3 years ago. And they are still in operation, running production workloads for our customers quite successfully. At scale, immersion enables zero water use. We collaborated with our partners in this ecosystem that we met at OCP in order to shrink down the actual form factor of the chassis by half. That's significant. We're able to get consistent, reliable performance from the servers in this immersion environment, and we also are able to work with our partners in order to achieve the 3 to 5 year warranties that are required. On top of it all, we recognize that OCP is a foundational place for us that allows us to accelerate our own development specifically for these technologies. We've leveraged significant amounts of insight and guidance from the community in the areas of immersion cooling and cold plate and rack and power and facilities, thinking about designing for a constrained data center, which is what we're operating within, with new or novel technologies helps us to de-risk our overall technology program. When we talk about infrastructure efficiency, one of the key metrics is power usage effectiveness, or PUE. The global average for PUE is about 1.58. At Denvr, we're achieving less than 1.04, and we expect that number to continue shrinking as TDPs for our servers actually go up. The more utilization you have in our data center, the better the PUE. Energy savings like this unlock capability, capacity, agility, and also significant TCO savings. So that, in my mind, is strategic co-optimization in progress. From the ground up, the infrastructure, the hardware, all of the support components at that data center layer, all co-optimized in order to deliver efficiency. Now, up until now, I've been talking about infrastructure and IT equipment, but the role of AI Neoclouds has evolved significantly over time, from providing raw GPU to now where we stand actually delivering a fully optimized AI cloud platform. Being vertically integrated can be very powerful, but it also can create a complexity challenge. For us, the balance is to focus innovation efforts where they deliver the most benefit and to leverage the open source tools from OCP and from our partners, from our ecosystem, in order to accelerate customer success. Now, as a nerd here on stage in front of a group of 11,000 of my closest collaborators, what I'll tell you all is that this complexity is really exciting for me. It's really exciting because there's a lot to learn, there's a lot to innovate on top of, and there's a lot of opportunity for collaboration. In an AI Neocloud, you cannot do it all yourself, and that is truly where the value of OCP comes in. So the complexity of where AI Neoclouds sit in this ecosystem, I think, is at the forefront. But the reality is that as long as you focus on the priority innovation areas, there's a lot of opportunity for us to collaborate. Shifting over to a second AI challenge, successful outcomes. Let's be honest, advanced technology is not it's not enough just by itself. It's really exciting to talk about, to stand on stage here and tell you about, but it's not enough. So MIT released a research study earlier this year, and what they said is that while very, very many enterprises are investigating AI today, very few of them have actually implemented it successfully. Those success stories, importantly, came when those enterprises were working with a partner, an enabler, a capability builder. That is a really, really critical piece here. And at Denvr Dataworks, we want to be that partner for you. We want to help you on your journey. There's a disconnect today in helping customers actually achieve those successful outcomes. We're in the early stages of AI. It's evolving very quickly, and many of our customers don't actually know what they need to do to get to that destination that they're striving for. So this leads me to our AI Ascend program. This is something that's really exciting at Denvr. It's a new program that we've created that helps to meet users where they are on their AI journey. We recognize that this area is evolving. We recognize things are moving very quickly, and we commit to our customers that we'll evolve alongside them. This approach has been very successful for us because it's a very customer-oriented and customer-optimized experience. The goal is to provide purpose-built AI, compute, infrastructure, and platform services with a very, very straightforward discount model to really meet those customers where they are. And here's where it is all very exciting for us. This is where all of our infrastructure investments, all of our orchestration, troubleshooting, all of our customer consultations all pay off. And it leads to something that makes me really excited. I love to see this type of customer success story. It's the result of an ongoing partnership between Denvr Dataworks, the University of Alberta, and the Alberta Machine Intelligence Institute. In this scenario, what we saw was that, our partners had an idea. They had a challenge and a problem to solve. And on top of the Denvr AI platform, what they were able to do was to deliver a very powerful tool. They improved ER care by developing an AI scribe on Denvr's platform. This AI scribe helped to actually automate the notation process for ER physicians. And in doing so, it reduced physician burnout, and it improved patient outcomes. This type of innovation is something that's happening every day in the AI space. It's one of many success stories that we have, but it truly, I think, is a demonstration of you have a brilliant idea, maybe you don't have the platform to get there, maybe you don't know exactly what tools you need to get there. Partnering with somebody can help you to accelerate your journey. The last thing that I want to mention is how OCP has accelerated our journey at Denvr Dataworks. We really have taken a lot of guidance and feedback. We've contributed quite a bit in this ecosystem, and we're very proud to call ourselves members here. I want to say thank you to all of the workstream leads and contributors who have helped us along the way. So here's the invitation. Let's work together. Join our sessions this week, test drive our products, collaborate on our solutions, become a strategic partner, and together with OCP, we can accelerate what's next in AI. Thank you all.
Please welcome BP Castrol Global Head of Data Center Technology, Sung Kim, and Microsoft Senior Product Manager, Shruti Sethi.
Hello and welcome, everyone. I hope you are having a lot of fun at OCP and already leveraging the great infrastructure that OCP sets up, the great ecosystem that it sets up. I feel extremely lucky and honored to be here today, especially because of the topic I'm here to talk about. OCP, of course, works on all of your effort, time, all the specifications, contributions that everybody makes. And a part of that are the innumerable contributions that our women contributors bring in. I'm especially here to highlight that very important part of the OCP engine. Have a good look at the slide. The names over here are nowhere close to exhaustive. We have so many women contributors who have been giving all of their effort to make OCP and specifications happen. They are across various communities of OCP: cooling, networking, security, storage, sustainability, and goes on, across more than 12 communities of OCP. I would really like to thank all our women contributors for managing everything and making such contribution and things happen. Request everyone to give them a big applause, please. With so many women contributors, OCP is also building the support system that they have. And Sung will talk about it.
So we thought it would be better that we have a more organized voice and approach representing women within OCP, which is a very influential and powerful organization in this industry. So thanks to the support from OCP, we initiated this group, Women in OCP, end of last year. Our mission is to address shared challenges and barriers across the industry at industry level. and also foster more diverse and inclusive ecosystem. This is our year 1, and our focus is to build safe and supportive community and village. So we support each other when going through life and career transitions. I personally came from oil and gas business, and when I first entered this data center tech industry and came to OCP, I was very overwhelmed by all different languages and culture. This will happen to anyone at least one time. Also, sometimes we go through life changes, such as parental leave, and may need to re-enter this industry at some point. And some folks goes on leadership track. So our aim is to really create a role model and challenge help people challenge the stereotypes here. We also talk and learn from each other within this village. With that, this is our highlight of the key milestone and achievement in the last 1 year. We had a very successful launch of the WOCP, Women OCP, at the Global Summit last year. George, our OCP CEO, came and gave a speech, and more than 100 women and men attended and joined us for this breakfast session. Early this year, we established a leadership team. So in addition to Shruti and myself, we also have other leaders from other segments to ensure that we capture diverse thinking. Back in April at EMEA Summit, we had another networking event when we open up and share strong personal stories and experience each other.
Come July, we actually started a new series that is the Empower Hour. So as a part of Empower Hour, we are bringing in training, mentoring for women and non-women leaders, whether it is through training about how to speak on stage, or it is training about a technical topic. We are sort of trying to include all of that. So please let us know what you want to see. And our membership grew very rapidly after that. Thank you so much for everyone who is joining us. We are already 200+ members. Tomorrow, at the OCP Summit, we actually have 2 special events. One is Women in AI panel. That's also co-sponsored by NVIDIA and Lenovo. And the second one, tomorrow at 5 p.m., is the WOCP networking session. We would invite everyone to please come join us and network and leverage the session over there. Finally, here is the invitation. Please join us. Help us build an inclusive tech community. Help us support women and non-women together and make it a great place for OCP innovations. Thank you.
Please welcome Intel Chief Technology and AI Officer, Senior Vice President, General Manager, Sachin Katti.
Thank you, Shruti and Song. That's a great initiative they just talked about. Great to be here, and thank you for joining me today. This feels like our community. This is our village. So it's great to be here amongst you all, amongst industry, and all of our ecosystem partners. So before I start, I first want to say a heartfelt thank you to OCP. It's been more than a decade, a tremendous collaboration, and a purposeful engagement that has led the industry towards open, modular, efficient, and scalable technology solutions. A number of previous speakers have touched on all the great impact that this community has had on the industry. I'll pick on one. For example, DCMHS, that we have been heavily involved in with the whole community over the last 3 years, really paved the path for building open, modular compute platforms for the data centers. It was a joint collaboration across chip vendors, across OEMs, across cloud partners, in fact, the whole industry, and really opened up the data center architecture. We are in another transformative moment in industry right now. Very exciting times, a big disruption, something that happens once in a few decades coming our way with AI. And I think a similar challenge is upon us. How do we help the industry? How do we come together and help the industry build these kinds of open, modular AI platforms for the future and deliver the scale that's needed to monetize AI and transform both our day-to-day lives as well as the businesses that are out there? I'm excited to touch on that topic today and how Intel plans to play a role in that transformation, what's required as we step into the next phase of AI from silicon vendors like us, as well as how we build a whole ecosystem around us so that we can deliver to the whole industry. So as we think about it, one question that I get in light of all the recent announcements from Intel, we've done a lot of partnerships, a lot of strategic deals. What is Intel's strategy in AI? I think put very simply, Intel is doubling down on AI. And the approach we are going to take is a very open approach. We are going to figure out how we embed every part of our technology stack into AI products that we'll use across the entire spectrum. It starts with the AI PC, bringing AI at scale to all of our personal computing devices that we use every day at work, and making sure that AI is accessible for our day-to-day productivity tasks. It starts with our CPUs. This is especially our collaboration with NVIDIA, where we want to make sure that our world-class CPUs are in every AI system that are going to get deployed out there. And today, I'll talk about how we are doubling down on our own AI systems. So we're not stopping at CPUs and not stopping at AI PCs, but bringing our own GPUs, our own accelerators, but with an open systems approach so that we provide customers choice and flexibility as they build out their AI infrastructure. So think of it as one step at a time, our technology being introduced into every AI system out there, but with an open approach that makes it easy for customers to adopt our technologies into the AI systems they want to build and deploy. So let's dig in. What does that actually mean? So one of the changes with new Intel, as Lip-Bu has come in, is to drive ruthless focus. Instead of trying to build for every workload out there, what's the workload that we're going to focus on, and what's the workload that we will deliver the best experience for customers to? And that workload, our focus is increasingly going to be on inference and agentic AI. Now, if you step back, I think as we have seen the hundreds of billions of dollars of investment that have happened and will happen over the next few years, a question that's prevalent in the industry today is, how will we monetize all this investment? How will society gain the benefits of all of this AI investment that's happening? We strongly believe that's going to be through agentic AI. It's going to be through agents that transform our daily lives. It's going to be through agents that transform how enterprises operate. That's how we are going to monetize and realize the benefits of all of the AI investments we have made and we will continue to make over the next few years. Now, this is not surprising. We are already seeing this happen, right? Google just reported a few weeks ago that they are now at 1.4 quadrillion tokens per month. That's an incredible number, right? That has grown by more than 100x in just over a year. The amount of tokens that are being produced, insatiable appetite for these tokens by everyone who is consuming these services. And this kind of explosive growth, exponential growth, means that we really need to figure out token economics. How do we deliver these tokens at scale? How do we deliver intelligence effectively at scale so that the whole world can benefit from AI? Now, if you step back and look at where we are today with inference and agentic AI, right? Today, we all use chatbots. They have become the dominant interface for consuming AI. And it's typically a single large language model that you're talking to. And it's deployed on a homogeneous, vertically integrated system today. Increasingly, over the last few months, we have all become familiar with reasoning, with chain of thought models. And those talk to themselves. They're generating a lot of intermediate tokens. And that just means even more tokens need to be produced, at least an order of magnitude, if not 2 orders of magnitude more. Now, if I extrapolate this to agents, it's even more. It's not just one LLM reasoning with itself. It potentially is multiple models. It's tool calls. It's data processing. It's a variety of tasks. and the number of tokens produced will just continue to explode, probably 2 to 3 orders of magnitude more. But the prevailing architecture of how we deploy these applications today is on a homogeneous, vertically integrated architecture that is stitched together using proprietary networking and proprietary software. We don't think that will scale. Effectively, you have to pick the highest and the most expensive compute component. You're locked into a vertically integrated architecture, and that effectively means that the performance per dollar that you're getting is going to become very hard to scale. There's no flexibility in optimizing the architecture to what your needs truly are. But if you look underneath, if you tear apart the veil and look what's actually happening in these applications. And this is also the new approach we are focusing on at Intel, really drive a workload-driven approach and understand what's happening in each piece of the workload, and then figure out what hardware to build. So for agentic AI, what does that mean? Typically, an AI agent is no longer just one LLM anymore. There's a huge component of context generation. All the prompts we need to create, the data we need to pack into these prompts, that's a big component. We have multiple reasoning models potentially, and even a single reasoning model, a single LLM inference call, you can think of it as 2 stages, prefill and decode. Prefill requires a compute-optimized accelerator. Decode requires a memory bandwidth-optimized GPU. So even a single LLM no longer looks like one monolithic application. It has different stages and different requirements. Then increasingly, these agents need environments, sandboxes. Think of a coding agent like Cursor. It wants to spin up a VM to test the code that it is producing and to see how it needs to iterate through that. Those require CPUs. Increasingly, you have tool calls with MCP. You want to search the web. You want to call an API. Again, tasks that need to run on a CPU. Finally, guardrails and security, so that you want to make sure that the agents act safely. They don't interfere with each other. Something that you might run on a CPU or even a DPU. So if you look at this landscape, if you tease apart this workload, very diverse set of components, and each one of them has very different compute, memory bandwidth, and networking needs. A one-size-fits-all, homogeneous, vertically integrated architecture does not make sense. What you really want is a more flexible, open, heterogeneous infrastructure, where you can pick and stitch together the right-sized compute, memory bandwidth, and networking together, and build those flexible systems that are customized for the agentic workloads that are coming at us at a furious pace. Now, the challenge, of course, when we talk about heterogeneity, when we talk about flexibility, modularity, and openness, is software. How do we hide the complexity of such heterogeneity underneath from the applications on top? That's going to be the key to unlock this kind of flexibility and heterogeneity underneath, so that there's zero friction to applications and to developers. That software needs to abstract away these underlying heterogeneity and make sure that it can take advantage of these flexible architectures when we put together all these different kinds of compute, different kinds of memory configurations, and networking technologies together. So this is what we need to do to first unlock even an open systems approach. Build this unified software stack, and then build the systems infrastructure underneath to actually build such open, heterogeneous systems that are customized and tuned for agentic AI workloads. That's our mission. What we will be delivering at an annual cadence going forward is such a scalable, heterogeneous systems approach, an open systems approach. Starting at the bottom, giving you choice, allowing you to flexibly stitch these together into open systems that can bring the right combination of CPUs, GPUs of different flavors, whether they're compute optimized or memory bandwidth optimized, stitched together using open Ethernet-based networking. Next, a system infrastructure that gets it ready in enterprise-ready form factors, as well as hyperscale Neocloud form factors, depending on the kind of capacity and requirements that you have, all stitched together using open networking technologies. And finally, this software stack that's going to abstract away the underlying heterogeneity and make sure that these applications work out of the box on such an open heterogeneous infrastructure. Spending 30 seconds on this software, our contract here is that developers should not change anything. If they are building on PyTorch, if they're building on Hugging Face, if they're building on LangChain, it should just work. And the key to this is a compiler and orchestration infrastructure that can tease apart the agentic workload, place the different components on the right kind of hardware, and stitch it all together to deliver that end-to-end SLA. This is what we're building. This is what we'll be coming out with in Q4 this year. Now, this is not slideware. This is something that we are already beginning to benchmark. We'll be talking more and more about these benchmarks in the coming few weeks. But it's just to stress test this. We put together an open systems architecture where we connected NVIDIA GPU systems with Intel accelerator systems and deployed this software on top to run a Llama model. And here it is the simplest form of heterogeneity exploitation, right? You run the pre-fill part of the Llama model on an NVIDIA system because those are compute optimized, really well compute optimized. And you run the decode part on the Intel accelerator, which have quite a bit of HBM and quite a bit of memory bandwidth. Even this very simple orchestration and simple heterogeneous system stitched together using Ethernet at the systems level delivers at least a 1.7x perf per dollar benefit for the same workload compared to a homogeneous vertically integrated system. This is in partnership with our collaborators at Gimlet Labs. They're bringing such systems together, leveraging our partnership. Now, as I said, the software is step one. The software is the key to unlock such openness, such heterogeneity. But of course, we need to continue to innovate on the hardware and deliver more and more choice at the underlying hardware layer so that customers have the flexibility to stitch such systems together. So I'm really excited to announce Intel's next-gen data center GPU, codenamed Crescent Island. This is going to start sampling in the second half of next year, and it emphasizes that focus that I talked about earlier. Inference optimized, agentic AI optimized, optimized for delivering the best token economics out there, the best performance per dollar out there. Few highlights. First, it's going to be low power. We are packing it with LPDDR, quite a bit of memory in LPDDR, very good compute for that memory capacity and memory bandwidth, so a very balanced machine for inference and agentic workloads. Built on our general purpose programmable GPU IP, XE3 IP. So this is fully programmable using standard tools. And this supports all the range of AI applications that you could think about. Coming back to the heterogeneity point, this is a very well-optimized GPU for pre-fill workloads. Has that right combination of the compute optimization that you need and just the right combination of memory capacity and memory bandwidth. We'll be talking more and more specs in the coming few months, but super excited to announce this. This is coming out, and this is sampling in the second half of 26. Now, the GPUs are one piece. As I said, for agentic workloads, the CPU plays a critical role. So many components of that agentic workload are going to continue to run on a CPU. And x86 is the dominant CPU platform out there. Pretty much any enterprise application you can think of, any enterprise database, any tool that you can think of runs and is optimized on x86 today. And I'm really excited to report on the progress we have made with the whole ecosystem over the last year on the x86 ecosystem advisory group. This has been a fantastic collaboration, again, an open collaboration with AMD and many other partners that have joined that are working hard to standardize and make sure that there is a lot of compatibility across the entire x86 ecosystem. Just a couple of successes to highlight. One is Fred. This is one where we collaborated closely to make sure that interrupt handling is standardized across the entire x86 ecosystem. So customers enjoy that compatibility. Second, AVX10. So collaborating on making sure that we standardize that instruction set and customers don't see different behaviors across different x86 platforms as they leverage these vector instructions. Over the next year, we will continue on this collaboration. We will continue to be adding more members, but increasingly soliciting what are the pain points from customers. Where are they seeing fragmentation? Where are they seeing challenges around software compatibility? And making sure that we take these into account, again, work with the whole ecosystem in driving an open, performant, and standard x86 architecture for the whole industry. Putting it all together, again, an open heterogeneous system with a software layer, choice at the accelerator layer, GPUs optimized for different parts of the workload, and again, an open x86 ecosystem to bring it all together into a flexible AI system. Now, when we put these systems together, the key piece is going to be how we network them, how we build those systems, how we cool these systems. And here again, excited to be part of this community, the effort that has been kicked off around open AI systems. I think critical for the industry, critical for this vision of agentic AI. I think we strongly believe that the future of this AI infrastructure is more open, more flexible, and heterogeneous. And the way to unlock that is through this kind of effort where we define these standardized networking technologies based on Ethernet that allow us to stitch together all of these different components into these optimized racks, have standardized ways of defining these racks, as well as cooling these racks, and then, of course, the software ecosystem around us to build this kind of compatibility with these open systems. That's going to be a critical piece, and we are super excited to be part of OCP as well as these complementary efforts that are stitching all of these systems together. So as we step back, one thing that's consistent across our work, and if I've not used the word open enough, let me use it once more. It's really how do we bring the whole community together? How do we do what we have done on the data center standard compute side for AI compute? As the workload changes, as the workload evolves to inference and agentic AI, I think the call for the day is how do we build these kinds of open, flexible systems that give customers choice and allow them to stitch together the kind of compute that they need for their workload. This is our commitment. We are going to do this across every layer of the stack, across software, across systems, across silicon, and bring it all together in partnership with all of you to deliver on the future for AI. Thank you again, and it's great to be here.
Please welcome Meta Vice President Dan Rabinovitsj.
Hello, everybody. Great to be here. This is such an exciting event. I can't believe how lucky we all are to live in this age. And I'm very, very grateful for all the great work of the OCP community. So brief just explanation of what AI means to us. We have a very large surface in Meta, and we have the pleasure of serving 3.4 billion people per day on our platform. But it also comes with a lot of responsibility and a lot of challenges. And today, I wanted to share a little bit about how difficult it is to scale. AI is used across all our apps, and I think this was brought up yesterday by Microsoft. We've managed to integrate AI into almost every surface and everything that we do as a company. And that has taught us a lot. But the scaling has actually been really, really fast compared to what we expected. We started using AI because we wanted to use AI to make our platform safer. So we used it to get rid of malicious content, harmful content, and then we started to see the benefit of AI to better serve our customers with better ad ranking and recommendations. But then LLMs hit, and everything exploded, and it became a completely different game. For us to continue to invest the way we were made no sense. So we had to put the afterburners on. And going through the journey from Llama 3 to Llama 4, we just realized that everything that we thought we knew about scaling was going to be a new adventure and a new journey. And as we look forward into the future, we just see more of the same. These challenges are real. So let's just call it. AI is amazing. The things that we're able to accomplish already in the very early days of artificial intelligence shows us the promise of what all this technology can deliver. But it is hard. Like, all of us in this industry have struggled. We've all made missteps. We've made mistakes. We don't get it right the first time. We should be humbled at the face of these challenges. We shouldn't be like overconfident that we're just going to keep making progress at the same pace. The humility is actually really helpful. But the motivation to keep going is because we have such promising results from such an early period in the history of AI. So this is really an exciting journey, but man, it is hard. And I used to just think, hardware is called hardware because it's hard, but actually, it's all hard. And kind of to illustrate that, we started very humbly with small GPU clusters. We got all the way to building a single cluster across an entire data center. And we thought, wow, this is great. Every time we doubled the number of GPUs, a bunch of stuff broke. We had to build software to do all kinds of careful checking. We developed a whole notion of server karma, which I talked about a couple of years ago, which basically predicted whether servers were going to get flaky, in which case we would take them out of a training job before we ran it, because reliability is so important. But then we quickly said, hey, why don't we connect a bunch of data centers together to do training? That was region scale. And where we're going next is even more bananas. And if you think that it's just going to be some kind of like walk in the park to go to now multiple regions, hundreds of kilometers apart, and make all that work at scale, no, it is not. This is actually really, really hard. And it's going to take innovations across every part of the tech stack, software, hardware, all the way down to transistors in custom silicon and all of the third-party silicon that's available. As part of this journey, just recently, we introduced the MiniPack 3N switch in partnership with NVIDIA using their 51T Spectrum X technology. And we had the idea that we needed to build a new generation of scale-out fabric, which we call NSF, or non-scheduled fabric, just to address the challenges of building these massive clusters across such huge distances. We needed a way to just guarantee that that performance would be delivered end-to-end. Now, how big is big? This is always like, this is fun. OK, we have two big projects that we've announced. One's called Prometheus, which is in New Albany, Ohio. That's a gigawatt-plus cluster. It's already up and running. I call this one flexibly assembled. For lack of a better way to think about it, we build, let's say, conventional data center buildings, and then we built a bunch of what we're sitting in. Please look around. This is a giant tent that we're in right now. We are building data centers in this exact type of structure. And we did it because we wanted to go faster, and we didn't care about the challenges that would be imposed on us technically. We went and solved all those problems operationally so that we could actually go way faster. It takes a lot less effort to build a sprung structure tent like this than a conventional building. And we're going to keep doing it. And then, to make the cluster even bigger, we started working with colos and even cloud service providers that might have capacity that was regionally proximal so that we could build a gigantic cluster. And that's what I call flexible thinking, right? We were flexible opportunists. We looked at every possible way to build capacity. Hyperion, which is in Richland Parish, Louisiana, is a 5-gigawatt center that will be purpose-built. We don't need to do flexible assembly there. We are starting from a white sheet of paper, and we are building that out as a gigantic, massive, single data center that will support 5 gigawatts. And how big is that? Well, if you started in lower Manhattan and you walked north of Central Park, it's about a 3-hour walk. Well, maybe some people could do it faster. That's the size of Hyperion. So physically, this thing is massive. And you can imagine just how much planning and effort is going to go into actually deploying all this capacity in a single location. All right. One of the other things that's happening with scale is that we have a diversity, a mix of different types of hardware. This imposes a bunch of challenges for software people, just as some of my peers and friends here have talked about. Like, we have to abstract a bunch of this complexity away from the developer community, both software developers, ML engineers. But the reality is, we're doing this diversity for two main reasons. One, we want resilience and diversity in our supply chain. We're too big not to have multiple options. And two, we recognize that sometimes we find a sweet spot where we can take a certain kind of hardware and deliver special performance for a particular kind of workload. And these two things will continue to come in play over time. I think part of scaling at really massive scale means you have to deal with a lot of complexity, and the trick is how to hide it. At the hardware level, we try as much as possible to avoid new, unique, and different things on every platform. We share rack common hardware as much as possible. We share as much as we can. And of course, all of that is under the auspices and through the genius of OCP, right? So we're taking advantage of all the reusable parts that we can to try to abstract that complexity. Now, I'm going to switch over to networking just for a second, because I want to talk a little bit more about this level of complexity. If I start from the right side of the picture here, scale out is super well understood in terms of standardization. Okay? This is Ethernet. 802.3 has been around for a really long time. We can make changes to that at the protocol and MAC layer if we want to get certain kinds of performance. But scale out has scaled because Ethernet is such a well-recognized standard. Everybody understands it. If I go to the left side and scale in, this is a work in progress, right? So today, you can use a bunch of proprietary interfaces to connect chiplets to each other. There's some really interesting work going on here to standardize interfaces at the silicon level. But today, you can get away with doing something proprietary. Over time, that will be a weakness. As Mark Papermaster said yesterday, openness wins. And we believe that even when it comes to silicon interconnect. Now, scale-up is actually becoming very critical for AI workloads. And I want to talk about this because today we are also struggling in a world where we don't have open standards. And I'm going to talk about that in some more detail later. And scale-up is very simple, right? We started with just a few nodes where we had to make sure that they could talk to each other. And that quickly propelled from 8 up to 72, 144. And we're going to much bigger numbers right now. And why? Why are scale-up domains getting bigger? Well, part of the issue is we're building silicon that is really dense in flops. We have a lot of compute density. And if you want to torque convert all that power on the compute side, you have to balance it with network and memory bandwidth. And larger scale-up domains help you to do that. And in finding that sweet spot actually has driven all of us on the systems engineering side to determine that we actually need larger scale-up domains. Additionally, the emergence of mixture of experts, which a lot of people have talked about this week, when you have hundreds of experts that are getting routed, they actually want to live in a low latency environment. So they want to be in the same scale-up domain. So this is what's happening. So it turns out, when you look at this, you got to go to bigger racks. And some people have asked me, like, why are you building big racks? Are you insane? It's like, well, the only way we can do that today is by having an electrical backplane or midplane or ortho connection. So basically, you have to stay in copper right now. And that is driving us to build big racks. Here at the show, you will see in our booth, Open Rack Wide. This is a great collaboration. You will also see on the opposite side that AMD has their Helios, which they announced yesterday. These are the same thing. We are building on OCP technology, contributing all this into open source. But to get to this double-wide mobile home of a rack, it took a lot of effort. And where we're going next is even bigger. So, stay tuned. Spoiler alert, yes, the racks are getting even bigger. So getting back to that standardization topic, we are really happy to announce that we're supporting the Ethernet for Scale-Up Networking initiative through OCP, ESUN. And additionally, we continue to be very bullish on Ultra Accelerator Link, UAL, and UEC, the Ultra Ethernet Consortium. All of these actually are important for us, and they're equally important because we want to see scale-up become open. This technology is too critical for AI systems. We know that over time, as this gets standardized and it gets open, we're going to see a flood of products coming from all of the partner ecosystem here in OCP that will serve this technology domain. All right, but big racks are challenging. We know we got to go there, but they're hard. They're hard to design and manufacture. They're expensive to transport. They're operationally challenging. Serviceability of these giant racks is tough. We found out you can't put this rack on casters because it actually violates the kind of mass per square meter of most manufacturing sites and data centers. So we've had a really important series of discoveries around all of the complexity of building big racks. By the way, just imagine if you have a 60, 70-pound tray, the sag that might occur in the middle of that tray is actually very challenging. These things are so big. So you have to structurally build everything in a kind of different way to get that rigidity and integrity that needs to be there as you're moving these racks around. They're all liquid cooled. They've got a lot of, let's say, expensive and fragile equipment inside them. So the care taken in this design is actually really, really impressive. Now I'm going to let you imagine in your mind what a BFR is. Okay, I think most of you got it. This is our reality today. BFRs are what we're building. But the future has to be disaggregation. So we are plotting a course out in time in the next few years when we will be able to see peak rack power density and then the decline of that peak rack power density because we'll be able to disaggregate using optics. Today, we are absolutely tied to the limits of copper in these scale-up domains. We want to be able to depend on optics, which gives us a lot more freedom to drive larger scale-up domains over a larger surface area in the data hall. This improves a bunch of stuff. If you think about the worry that we might have to strand power in the data center, it's because you have a fixed amount of power per row. We want to make the rack power granular so that we don't risk stranding that precious power, which is such an important resource. So optical disaggregation is going to be really critical for us. All right, so we're moving from massive to ludicrous scale. That's really what's happening here. And I don't want to make this just about meta. I'm just putting this slide up just to kind of show you, just in our little world, this is kind of like the insane amount of capacity. And the Richland Parish site in Louisiana, that's just one 5-gigawatt center. We're going to build a bunch of these. And the entire industry is building a bunch of these. That's the really key thing. We're not alone. All of us are building at massive, massive scale. We need a ton of power. This journey is impossible by ourselves. We have to continually bring creativity and energy into solving how do we actually deliver this amount of capacity. And every time I ask, do you really need that amount of capacity? Are you crazy? The answer is, you better start building because we need more than you think. That is actually what's happening. The research community, the people who are building the models, understand that they need more capacity faster. As my peer from Oracle Cloud said yesterday, velocity is really important. He's not talking about speed and performance of the silicon. He's talking about speed to deliver capacity. And that's a massive challenge for us. So what's happening? We are delivering supercomputers as if they were like a mass-produced product, right? It's just completely nuts. We used to think that, you'd see these great supercomputers coming online in, in places like Argonne Labs and JPL and stuff. Those would take more than a year to kind of build, stabilize. They were artisanally crafted. People were running around tweaking them. We're now doing this like hundreds hundreds of supercomputers mass-produced per day. And we've shrunk the design cycles to be about a year. So silicon life cycles now are about a year. Building these giant supercomputers at a year, we're really now transforming infrastructure to be like a consumer electronics play. This is just completely bizarre. We're used to a new phone or a new television coming out every year for the holiday season. Now we're doing the same thing with supercomputers. This is really, really hard. So it's unprecedented complexity, an insatiable need for growth, and yes, I know there's a lot of questions about the bubble, but for the next couple of years, we have line of sight to actually needing and deploying all this capacity. So we have to deliver it, and we have to deliver it with quality and reliability. We can't just throw a bunch of stuff out there and say, well, I spent $100 billion, I sure hope it works. No, like we have to engineer all of this to be quality product that can be used immediately when we hand it over to our product groups. The operational complexity of bringing up a heterogeneous fleet is prodigious, and we have to do this all at higher and higher velocity. I'll give you an example. You'll be able to see this in the Meta booth as well. We had to design a brand new tug just to move these big racks around, and we're going to open source that design, so that will be part of an OCP contribution as well. But you can imagine, like, we didn't think operationally that we'd be moving the equivalent mass of an African elephant around as a single rack in a data center. That's just not something that we could have imagined 2 or 3 years ago, and we're actually doing that right now, and we're having to build all of the tooling and all of the software and all of the hardware capability to do that. Even just liquid cooling in data centers is imposing a significant amount of operational complexity. So we need this ecosystem to be more vibrant than ever before. So power generation is the industry's Achilles heel right now. We need more power. I feel like I'm Scotty on Star Trek, but Captain, we need more power. We need a lot more power. And what's really interesting, and I want to really build empathy for our manufacturing and design partners, the ODM community, the contract manufacturers. Every 10 megawatts of capacity that we deliver in a data center, they need to build a megawatt of capacity just for testing. Now think about that. We haven't asked this community to invest like that ever. And we're asking them to invest together with us because this industry has to keep moving fast, and we need to keep putting the pedal to the metal in terms of being ready for all this engineering complexity. Which brings me to the expertise problem. We are really starved for quality engineers across the industry, and we're looking also at all of our partners. They need to be able to hire skilled workers in all these factories. It's not like building a traditional scalar compute server anymore, or a storage system, or a network blade. We're actually trying to get people who have never looked at a complete liquid-cooled, crazy, megawatt power density rack and have to cable all that up with the thousands of cables and do that consistently and accurately and switch those lines up to deal with the heterogeneous fleet and a crazy mix of product coming out. So this is really a challenge for the industry. And finally, we need a lot of creativity and innovation. And I'll point out a couple things right now on this point. When you look at the challenge for greenhouse gas emissions for the entire industry, this is a tough problem, and everything I've said today just makes it even tougher. We're going to be building a ton of capacity. We need to look at very dramatic and creative ways to reduce the emissions associated with all of this infrastructure. So we're counting on this community to continue to invest in that in the future. All right, to summarize, having built infrastructure for years, we thought we had learned everything there is to learn about scale, but honestly, AI is kicking our collective butts. Every day, we have to stand up and figure out how to address these challenges. One of the most fun things about being at Meta, for me, is that we get to work on every layer of the stack, from PyTorch down to transistors, and that helps a lot with understanding the scale and the context of all these challenges. But what's most important for us at Meta is that we work in partnership with the Open Compute Project community, and we're committed to that. We will continue to contribute, and we will continue to enjoy the benefits of being in this wonderful community. Thank you so much.
Please welcome back Open Compute Project's Senior Director of Global Events, Kaylee Burdette.
I know we kicked off everything last night with our fantastic keynotes and our social, but now our week really begins, and we are thrilled to have you here with us. Of the 12 years of hosting the Global Summit, this is the first time we've had to move the keynote to a larger space. And looking out at all of you, it's such a tangible representation of not only how much the summit has grown, but the foundation as a whole. We have so many seasoned companies, new companies, startups, individuals flocking to OCP. And here to welcome you all is our small but mighty staff, our countless volunteers, and our members who help us facilitate the projects, work streams, and initiatives that we need to move our industry forward. OCP continues to be the home for rapid innovation, a force that's amplified in the age of AI. And today it's clear that the broader tech industry looks to OCP and our community to blaze that path. So on that note, we'll wrap things up. Once you leave here and cross over into the main building, lunch will be served and our expo hall will be open. Make sure to check out the Innovation Village and our emerging technologies demonstrations from our symposium. I hope you'll join us tonight in the expo hall for our Booths and Bites event from 5 to 7. And don't forget that after today, breakfast and lunch will be served here in the South Hall. This is also a great spot to network, take a break, check your email. This space will be available to you tomorrow and Thursday. If you have any questions, stop by and see us. We'll be happy to assist you. We want to ensure that you have an incredible experience here this week. We truly appreciate each and every one of you being here with us. Thank you. Have a great week.